grounded on non-linear dynamics. I now invite Professor Muktesh Acharya from the Physics Department of Residence University of Korea to begin the proceedings. So please.
Good afternoon, everybody. I welcome you all to the half-day conference on linear afternoon. That is basically organized by our students, and it's a conference. Basically, highlight the subject nonlinear dynamics. And nonlinear dynamics is a special subject which can be applied in various branches of science. For example, physics, chemistry, atmospheric science, and even biology. So today, in the plenary talk by Professor Dhruva Banerjee of Jadavpur University, he will mainly discuss the technical details, the basics of the nonlinear dynamics, the properties of the nonlinear differential equations, and after that we have two talks by our students Shobhadip Kundu and Shobhik Chatterjee. They will discuss the applications in biology. Shobhadip will discuss the applications in the bacterial respiration. So that is application in the microscopic aspects of the biology. And after that, the Shobhik will discuss it in applications in the evolutionary biology, which is looked and so I wish you great success of this program and thank you.
Thank you, Professor Acharya. I now would like to invite Shobha Das to deliver a few words regarding this conference.
Good afternoon. Warm welcome to you all. We are a bit late in this session. So, without wasting much time, I would just like to emphasize that this seminar was organized nearly entirely by the students of our department. So, we would like to acknowledge every one of us, of you who are involved in this, fellow students, and also the professors, Professor Acharya, Professor who have supported us for this process. The students of our department also organize a national level conference on condensed matter, materials and statistical physics, the CMSP, which has been held for the past 3 years. So held also this year in April. And a similar conference like this one on nonlinear dynamics was held back in 2020 during the pandemic. That was in online. So we are trying as our part of our student life trying to organize such events, and we hope to see your cooperation and support in the future too. I will not spend any more time on this. Speakers are waiting. So thank you all for coming, and let us enjoy this non-linear afternoon. Thank you very much.
Thank you, Shobha. Now let us begin our discussion session. The first session will be chaired by Olivia Molly, a PhD student from Presidency University, Kolkata. Good afternoon, everyone. Thank you for joining us today at this exciting seminar. We have a activity journey ahead of us exploring nonlinear dynamics. Without further ado, it's an absolute privilege to introduce our distinguished speaker, Dr. Dhruva Banerjee. He is currently working as an assistant professor at Jadavpur University. Dr. Banerjee did his post-graduation from Jadavpur University in 2000 and PhD from Indian Association for the Cultivation of Science in 2006. After PhD, he joined St. David's College, Kolkata. He He worked there for 2007 to 2008. From then onwards, he has been in Jadavpur University. His research interests focus on nonlinear dynamics and statistical physics. Today, he will be talking about introduction to nonlinear oscillators.
Thank you, everyone. Am I audible? So, which language will you prefer? Everyone comfortable with English, or everyone will prefer Bengali, whichever is your choice? Bengali or English? So, my topic of discussion, as she just mentioned, is nonlinear introduction to nonlinear oscillation. So, basically, this talk is mostly oriented towards BSc students who have just come from in their high secondary studies. So I'm not assuming any knowledge on the part of the audience, on that part of that fraction of the audience. So let me start with a very elementary thing. If I just ask you how to calculate the time period of a harmonic oscillator, everyone is comfortable with that? Say I have this is my so this is what I understand as the energy expression, right? Fine. So if I want to calculate, there can be several processes, but well, since this is a harmonic oscillator, at some point of time this x dot is 0, at x equal to a, this x dot is 0. So the energy there is completely potential, right? A being the amplitude. So you cancelling this m by 2 factor from both sides. This is a very elementary thing, but this particular technique will we will apply for nonlinear oscillators also. So if I cancel this m by 2 from both sides, we have this omega square a square minus x square. Okay, fine. So from this we have root over, sorry. So this is a square minus x square on this side, and this is omega dt on this side. Fine. So as I integrate, this is from 0 to capital T, and this one, it starts from 0, makes a full oscillation, and comes to this end at capital T, time capital T. So what is the limit of x integration? 0 to 0. So this is a symmetric oscillation. You have to make it as 4 into 0 to a. So that's the point, right? 0 to a, okay, 4 into 0 to a. So this is simple. I make this integration. This is a simple sine inverse. Okay, so you have this. This answer is simply obtained. This is sine inverse x by a. Makes it pi by 2. So we obtain this t as 2 pi by omega. As we all know, this is a very well-known result. But this particular result has another very important aspect with it. There is no amplitude sitting on the right-hand side. That's a fact. That's a very sacred gospel of entire physics. That this time period of harmonic oscillator is independent of amplitude. This fact does not carry over to nonlinear oscillation. That's what we shall be exploring now. Okay. So let me ask you. Suppose I am replacing this potential, this v of x, by a different, let me write it like lambda m by 2p x to the power of 2p. This 2p factor I am writing here because when I shall be considering if we consider the differential equation of motion, then this 2p will cancel. For a v prime x, this 2p will cancel. That's why this 2p is present in the numerator. Not no other significance is given here. But the fact is, if the potential is like this, can we calculate the time period? Okay. So this is what we are now we are focusing on non-linear oscillators, purely non-linear oscillators. So this is a non-linear oscillator periodic system again. You can understand if P is 1, this is harmonic oscillator, but if P is 2, so it's a more steeper confinement, right? So steeper than a parallel. So it's still it's a symmetric potential, but as you increase P, you make the track more and more steep. So that's the point here. So you write down the same, you follow the same process here, that lambda m by 2p, x to the power of 2p, and that is the energy, and that energy is being equated to the energy at the end where there is no kinetic part, and we have entirely potential energy, right? So this is simply the amplitude x equal to. Now you go on follow this procedure here. It is dx dt whole square again here, and cancelling m by 2 from both sides. We have lambda by p, a to the power of 2p minus x to the power of 2p. Vishnu, দেখা যাচ্ছে তো? A to the power of 2p minus x to the power of 2p. Now this integration dx by root over a to the power of 2p minus x to the power of 2p, and this is root over lambda by p dt. Again, you should not miss this factor of 4 by integrating this from 0 to a, and this is a very standard integral if you are acquainted with it. If you are not, I am doing it explicitly. Is this integral a non-integral for you, most of it? I am not expecting a yes from the basic first year students, but the senior students may have seen this integral. If you have not, you simply put this x by a to the power of 2p equal to something, call it say z. Okay. So on the right hand side we have this. Fine. So let me quickly do this integral before I come into meaningful conclusions. So this is for 0 to a, and not 0 to a. So let me do this thing first. This gives me x as equal to a z 2b, fine. So dx equal to a 1 by 2b z 1 by 2b minus 1 z. Okay. So when x equal to 0, z is 0. When x is a, z is 1. So it is 0 to 1. Dx is a by 2b. Z to the power of 1 by 2p minus 1 dz. And on this side we have taken a to the power of p outside, and here it is 1 minus z. Is this clear? Okay. On the right hand side we have root over lambda by p. So t will be obtained by doing this integration directly. Is this integration known to you? On the left hand side. This is a known integration for you. Anyone? The left hand side. It's an integration from 0 to 1, z to the power of something, 1 minus z to the power of something. Right, it's a beta function. So, I'm reversing the LHS and RHS just for my convenience with t. And here it is, this constants go out. This is, this 2 cancels. So it is 2 by p, a to the power of 1 minus p. And then we have a beta function. How is it looking like? 0 to 1 dz, z to the power of something minus 1, and this 1 minus z to the power of minus half, which I can write as half minus 1, right? So it is simply a beta function of say 1 by 2p and half. That's a number that reduces to a number because you can just evaluate it in terms of that product of gamma functions and all that. But that is just a number. That is not the point of interest now. Because it reduces to some number. It's a definite integral. My main point of interest is this: that the time period is now amplitude dependent. When P was 1, for the harmonic case P was 1, there was no amplitude dependence in the time period. But now there is a time dependence. But there is something more interesting here. I'm writing it like T. There is no necessity of evaluating this integral, though this is a very simple thing. It's beta 1 by 2p comma half. So that is equal to gamma 1 by 2p into gamma half divided by gamma of sum of those two arguments. So that is just a number. Point is that this time period is proportional to a to the power of 1 minus p. And if you now concentrate on this equation, a goes as e to the power of 1 minus 2p, 1 by 2p, okay? So that means it is e to the power of 1 minus p by 2p. So why this is interesting? It is interesting because, again you see, if p is 1, time period is independent of energy. What does that mean? Harmonic oscillator, fine. But now see, if P is greater than 1, as I was talking of steeper confinement, if P is greater than 1, then as E increases, you are pumping energy to the system. As E increases, time period decreases, right? Because the power of E is negative. It's 1 by E something. So as E increases, time period decreases. That means as you are pumping energy to the cell, it is oscillating faster. You have a greater P, greater confinement, you put energy into the system, it will oscillate yet faster. That's fine. But the point is, if P is lesser than 1, that is also nonlinear oscillation. If you have a flatter confinement, then what happens? Then as you pump energy into the system, time period becomes larger. That means you are giving energy to the system and it is behaving more lazily. Your time period is increasing. So where is energy going? There is no dissipation anywhere. So this is something very interesting in context of nonlinear oscillations. Let's explore this point. The answer lies in the distribution of kinetic and potential energies. You have heard a term like equipartition of energy in context of thermodynamics, literally statistical mechanics. Equipartition of energy is a very sacred thing we always follow in statistical mechanical context, but that is applicable for baths having harmonic oscillator properties. Okay, where the energy is equally partitioned between the kinetic part and the potential part. When the baths, in statistical context, we talk of a bath. Here we are not talking. We are talking of a single oscillator. Here also, we are not going into statistical considerations now. If time permits, I shall go. But the point is, if you suppose calculate the average of kinetic energy, I am not writing T for kinetic energy because T has already been reserved for the time period. So kinetic energy average over a full cycle. Okay. Over a full cycle means over a full oscillators, 1 by capital, 0 to capital. So that's the average I'm talking about. So 1 by capital T, 0 to capital T, half M. So this is the average I'm talking about. If you do this average here for harmonic oscillator case, you will just obtain half of this. That's a very simple integration. Okay. What we obtain here is, let's see what we obtain here. The procedure is also here quite straightforward. You this half n x dot square, you bring a dx here and a dx here. So that's a 1 by x dot into dx, right? So if you call it okay, in this step I should be writing a different integration. So let's not repeat the same thing. So it is m by 2t, okay. So I'm writing it now. T, this is x dot whole square. This is 1 by x dot dx, right? This dt part. Okay, dt by dx. So now this integration comes over dx. For that I bring a 4 here and 0 to a here. Okay, I should be cautious in making this change. Okay, fine. So here we have this like twice m by t 0 to a dx by x dot. What is x dot? X dot is already here, right? X dot is root over that part. So you write it like this is twice m by t 0 to a dx by this x dot is root over lambda by p root over a to the power of 2p minus x to the power of 2p. Okay, so this integration is again very similarly done. Oh, I'm sorry. Very sorry. X dot is what is it? Root over lambda by p root over a to the power of 2p minus x to the power of 2p dx. This also is very similarly done. Beta functions will come out because you again make the same substitution what I did here, right? X by a to the power of 2p equal to z, and you get a beta function. That's very simple. So that's this k becomes these constants go out twice m by capital T root over lambda by p. Is my handwriting legible from behind? Okay. I'm hurrying a bit because the time is not very long for this kind of derivation, but yet I chose to discuss this thing because I thought the students who are coming from who have newly joined here, if they be present here, they may find something interesting in this stuff. Rather than going into fixed point analysis on and all that, those are rather a bit alien for starting lectures. Fine. So this is 0 to a to the power of p root over 1 minus this is z, right? And what is dx? Dx is already obtained here. Dx is a by 2p eta. So this is a by 2p. The space is 1 by 2p minus z. 1 by 2p minus 1 is fine. Here. So we have this twice m by t root over lambda by p. Here we have a to the power of p plus 1 by 2p and a beta function. 0, oh no, sorry, this is 0 to 1 here when I substitute z, 0 to 1. So z to the power of 1 by 2p minus 1, 1 minus z to the power of half this time. Half means 3 by 2 minus 1, right? So you have to make this rearrangement, 3 by 2 minus 1 dz. So it's a beta function of 1 by 2p and 3 by 2. So we have some constant sitting in front, root over lambda by p, a to the power of p plus 1 by 2p, and this is beta 1 by 2p 3 by 2. So this is the average of kinetic energy. Understood, everyone? Is it clear? This is second clear. Any question? Fine. So now if you go to calculate the potential energy average, the potential energy average is similarly obtained as 0 to capital T. The potential energy was written as lambda m by 2p, x to the power of 2p right? Okay. And here again you make the same going over to x integration. Okay. So 1 by 2p lambda by 2p 4 0 to 8 x to the power of 2p by x dot dx, right? So dt is changed to dx by x dot. Again, you put the value of x dot here, twice m lambda by pt here, and 0 to a x to the power of 2p divided by x dot. What was x dot? X dot was root over lambda by p, root over a by 2p to the power of 2p minus x to the power of 2p. So this was x dot dx, right? So again you make the same substitution, twice m lambda by pt, all right. So here it is root over p by lambda in front of the integral. 1 by a to the power of p comes from this radical sign. And here it is 0 to 1, x to the power of 2p. X to the power of the substitution is x to the power of 2p means a to the power of 2. A to the power of 2p into z. Then comes dx. Dx is here a by 2p, z to the power of 1 by 2p minus 1 dz. And on the denominator we have root over 1. Constants go out. Constants means a to the power of p. Here is a 2p, here is a p. So again it's p plus 1. So twice m lambda by pt root over p by lambda a to the power of p plus 1. And anything in the denominator is 2p. In the middle. Anything missing? I think no. So here again we have a beta function, but a different form. Z to the power of what? This is 1 by 2p, right? So 1 by 2p means 1 by 2p plus 1 minus 1. So this is 1 by 2p plus 1 minus 1 and 1 minus z to the power of minus half, which is half minus 1, right? So it is half minus 1. So beta function of 1 by 2p plus 1 and half. So what is that amounting to? Have I spaced right? Okay, let me write it over there because so that this was the expression for kinetic energy average, fine, and the expression for potential energy average comes out to be twice m lambda by pt root over p by lambda. Is there a extra p here? No, this I think I have got an extra p here for this is here. Let me see. Probably this is somewhere 5. So this is a to the power of p plus 1. This is twice p. Beta 1 by 2p plus 1. So this is average. If you take the ratio of these two quantities, that's a whole point here. That if I take the ratio of the average kinetic energy and the average potential energy, what we obtain? Probably I have done the calculation, okay, but I'm a little uncomfortable with this one factor of p in the denominator. I don't know where this comes from. Let me see. So if I take the ratio of these two quantities, these two expressions, most of the prefactors cancel. You see, twice m lambda. This is a root lambda here, right? That cancels it. So if you just make these little arrangements, I think it's okay, right? No, it's okay. So let me write the prefactor correctly. Twice m by p root over lambda by p a to the power of p plus 1. Oh, this 2 factor also cancels anyway. This 2 was also present here. So the entire prefactor here is same. So if you take the ratio of the average kinetic energy to the average potential energy, the prefactors cancel. You have a ratio of 2 beta functions. Okay, the upper beta function is looking like b 1 by 2p 3 by 2. The lower one is looking like 1 by 2p plus 1 half. Okay, so if you can apply that very well known identity of beta functions, I can really, okay, fine, I can delete this part. So beta of 1 by 2p 3 by 2 is equal to gamma 1 by 2p gamma 3 by 2 divided by the sum of these two quantities, right? And beta 1 by 2p plus 1 half. That comes out as gamma 1 by 2p plus 1 gamma half divided by the sum of these two quantities, which is the same as the denominator of the previous one. So if you take a ratio of these two quantities, as I was taking, this is half gamma half, right? And this is 1 by 2p gamma 1 by 2p. Gamma n plus 1 is n gamma n. Okay? So what remains? Half gamma half. Okay? So here I write it as, I need some space actually. Let me spot, because so gamma 1 by 2p half gamma half is root pi. The denominators cancel, so this is 1 by 2p gamma 1 by 2p gamma. So this is simply these gamma functions cancel and you are left with p. Okay, so the kinetic energy and the average kinetic energy to the average potential energy values to what? This part I have written anyway. This is when P is 1, the case of harmonic oscillator, there is actually equivalence between kinetic energy and potential energy because both of them are the same ratio 1. But when there is disparity between these two quantities, that means there is some nonlinearity in the potential. And that potential, now you understand what is happening. The time period, and the time period was increasing with increasing energy. That was happening for P lesser than 1. That is because most of the part, when P was greater than 1. When P was greater than 1, this was coming to the denominator, and as you were pumping energy to the system, time period was decreasing. That's because as the energy was being supplied to the system, the partitioning was such that the most of the energy was coming to the kinetic part. But if it be a flatter confinement, partitioning tends towards the potential part, right? As you pump on energy to the system, the pumped energy goes to accumulates into the potential. So that's why the kinetic energy by potential energy when P is lesser than half, when P is lesser than 1, the average kinetic by potential energy is greater than the average kinetic energy. So whenever you are pumping energy to the system, the energy is going to the potential. So this is something very interesting in context of nonlinear oscillators. From this point, how much time do we have? 10 minutes. Okay. 10 minutes. dynamics means from this point I can go in several directions, but well, let me statistical mechanical point of discuss senior students, have you ever calculated a partition function? You have all calculated the partition function for t equal to 1, right? Have you calculated the partition function for t different from 1? Have you ever done it? So let's go to the statistical mechanical aspect of this problem. Have anyone done it? Actually, it is easy, but the point is you do not need to do this integral. There is a technique to escape it. Let me do it. So you have been given n oscillator. Suppose I am going into a very general version of the problem. So suppose I am writing a Hamiltonian, these are all non-interacting oscillators, first of all. Okay, there is no interaction between them. So it's a classical problem. So the Hamiltonian is like I equal to 1 to n. There are n oscillators. Okay? And I bring in some coefficient, say I for ith oscillator. Here it is pi. It's a very general problem. Let me write it as a here. For kinetic energy, actually a is 2. But for mathematical generality, I am bringing it here. And something like bi. Hamiltonian like this. A and B are constants of the problem. And pi, what is pi? Pi is basically it is pi1 square plus pi2 square plus, say if I consider a d-dimensional case, so it is something like this. Right? Similarly, we have this, I mean this magnitude. D-dimensional case, we were considering one dimension here. So in statistical mechanics, all the 3 dimensions are equally relevant. We can always, there can be 1-dimensional oscillators, there can be 2-dimensional, 3-dimensional oscillators. In statistical mechanics, we deal with more weird dimensions, but those are different considerations. Anyway, so this is something we have, right? So now you have to calculate a partition function. What is a partition function? Canonical partition function. So canonical partition function, this actually will be like h to the power of something. That should be nd. Okay. So here it is some dndq, dndp, e to the power of minus beta, this function, right? So this is something I'm considering for students who are acquainted with statistical mechanical ideas. There are several students from outside the research institutes I just heard. So there are some senior students also. Maybe the first year students are not acquainted with this formalism. So please bear with me for a few minutes, for the last few minutes. So this is what I am. Let me clear up this part. With all these x's, x1 square, s to the power of 2 by t, plus x2 square, s to the power of 2 by t, and so on. Right. So here you can make a little scaling. Just a little scaling will help you. So introduce some y1, which is equal to x1 s to the power of 1 by t. So that makes it y1 square. This is y2 square, and so on so forth, right? So x1 is actually x1, x2, whatever. So this is y1 s to the power of 1 t. This is s to the power of minus 1 by t dy1. Okay? So if you do this same thing here, we have, look, here we have, I have written it here, right? Pi means pi1 square, pi2 square, these are x1 square, x2 square, and so on. Something to the power of, here it is a here, so it is a by 2. Right? Similarly, here it is given this squares to the power of b by 2. Okay, just a little variable transformation will help you. So the a factor that was sitting in front, okay, that s factor, sorry. The s factor that is written, the basic technique here is you have isolated this s part. So how is it helping you? This s actually contains the beta. And rest part is not containing any beta. At the end of the day, you take a log. And that isolates the beta factor. And then when you do minus del then beta logs it, you only are left with the beta factor, coefficients associated with beta, and rest everything dropped down to 0 because of the derivative. They are not containing beta. You are just isolating out the beta. So this particular scaling is helping me to bring out this s. S is actually containing the beta in the integration. Right? So that is the technique. So for the P, say for the, let me do any one. Say for the Q part, the Q integration. How does it look like? This looks like dq. This okay. Okay, and here we have this. You understand now what I am doing? Okay, because for each for this, these are all Q's, right? These are all P's, so I have to write P. Anyway, so when we are doing this integration according to this particular technique, for each of these d factors, s to the power of minus d by t comes out, right? So s to the power of minus d by t comes out. So you have minus d by, what is t here? Beta ai, right? Okay. So this is coming out here, and the rest part is something you are not capable of doing. Say this is d yi e to the power of what you can say as minus yi1 square plus yi2 square. So this is an integration which does not contain beta. Right? Does not contain beta anymore. But here it is containing beta. Again, you have a similar expression for the Q integrations, which have this, here they will you obtain it like s to the power of minus d by beta bi, again an integration like this, which does not contain beta. Right, so when you are accumulating all of them together, and then you are taking a log, I'm out of time, you are taking a log, what happens is, just s to the power of this part minus minus t by beta 1 by ai plus 1 by ei. Kind of this thing comes out with the other integrations sitting. This do not contain beta. Now when you are taking this is z we are calculating. So when you are taking a log, so this is simply log of this plus log of this. And this log brings a beta down. So it's minus d by beta 1 by ai plus 1 by pi. Got it. This is the only beta part. And then we are taking minus del del beta. So when we are making a minus del del beta, this operates on this derivative on this expression only, that part drops down to 0. And what will you operate on here? Any idea? Oh, I am actually due to some hurrying too much, I have mixed up this s and this. This is 1 by t that is coming here, s to the power of minus 1 by t. So 1 by t is actually is minus s to the is actually s to the power of minus 1 by t. What is t? T is not beta I, sorry, t is a by 2. I'm sorry, I'm very sorry. So it is a by 2 here, and similarly it is b by 2. I'm sorry, because just because of going this side and that side, I have mixed up the expressions. Is it clear? Is it clear? So e to the power of the s to the power of minus 1 by t, which becomes s to the power of minus d by t. T is actually the exponential here, the power here, a or b. It is not b. So finally, it is simply this is 2 by a and this is 2 by b. Understood? Okay. So now you are taking a log of this part. S means what is S here? S is minus beta ai, right? So what? Sorry, S is beta ai. So beta ai to the power of minus b by beta 2 by a plus 2 by b, okay, plus log of something I'm not interested in because that does not contain beta. So minus delta beta log z as you are doing. Beta. Huh? This one?
So that d by 3, that is now there. So we won't have that beta.
This operation you are doing, right? Minus d by beta.
So that beta is not there.
Actually what?
So beta is already absorbed in. So we put there d by 2. So that is.
Oh, okay. So this beta is not there. Fine. So I don't know. I am actually hurrying too much. Anyway, this minus t, okay, beta ai plus there should be a beta pi for the other part also. The point is that when you are making this minus delta beta here, this part is this 1 by beta comes out from here actually. Okay, that is at, right? The most important part is 2 by a plus 2 by b. That's the factor I was aiming. The rest part is redundant, so I was not very much attentive on that part. This 2 by a plus 2 by b. Now you can see the equipartition very clearly. If a is equal to 2 for kinetic energy, let's now make a equal to 2. Let's take this 2 outside. This is, let's take this 2 outside. This is 1 by a is 1 by half. But 1 by b, if it is equipartition, is half plus half. And it is not. Then naturally there should be this is 1 by b some other factor. This is half plus 1 by b. So half plus 1 by b means the partitioning is not happening as it happens for harmonic oscillations. The b factor is taking away the potential energy part. Right? So this technique is a little involved. The time was relatively short, so I was hurrying a bit this side and that side. I'm sorry to be jumping up little here. Could have been done in a more relaxed way. Anyway, the main point I wanted to show you is this: that this factor can be brought out, and after taking that typical minus gen del beta log z kind of expression, you get the expression for energy where we have this 1 by A and 1 by B clearly separated out. 1 by A comes from the kinetic energy part, A is 2, and B from the potential. I'm ending here because I think extension of this talk can be made in various directions, but that's a different consideration. Otherwise, I did not have the statistical part in my plan. It just because for the last 10 minutes, I could not have gone to perturbation techniques and all that. So that's why I chose to do this. Anyway, any question you can ask and we can discuss.
Please raise your hand if you have any questions.
If you have not, we can discuss later also because the other speakers are also waiting. We can discuss definitely later. If you have difference actually. These are yet not textbook materials as far as to the best of my, but well, for nonlinear dynamics, Jordan Smith, of course, a very, very good reference. Jordan Smith and Stokes, of course, is the most widely followed by. Jordan Smith is a more mathematically rigorous book. You can go into that book where there are very tough problems and you can have a very good time with it. Very highly detailed Jordan Smith. An introduction to nonlinear differential equations, something like that. Jordan and Smith, J-O-R-D-A-N, Smith, S-M-I. Okay, if there be no other question, if you have any other question, we can discuss later on because we have already started late. There are other enthusiastic students who will be giving talks. So we'll do it. Thank you.
Thank you, Olivia and Professor Banerjee, for such a fascinating talk. Now we go ahead towards the student discussion session. This section will be chaired by Shobhata Mishra, who is a PhD student from Presidential University, Kolkata.
Now, the session is followed by two students talk. First one is given by our postgraduate semester 3 student, so he will talk about physics behind the bacteria. How does the bacteria respond? Good afternoon, everyone. We just have a talk on linear oscillators just now, and this bacterial respiration I will show that how does the oscillation happen in the bacterial system or the real time system, and the output of the last side basically of this talk is also an oscillation. So, as per the title of the talk, you can see that how does bacteria respirate? The bacterial respiration system is basically an approach to nonlinear dynamics. And in the talk, I will first come out the biological point of view. What happens in the bacteria? The real life bacteria. And obviously cultured in a lab, but it is the in vitro lab and we have done it. Then what are the experimental results we have got from the various people who have collected? And then the mathematical approach where the true nonlinearity is happening. And then the future and the references. Then what happens in the biological phenomenon? As per we can see that we know that all the living organisms are basically broadly split into two parts. One is prokaryotes and another is eukaryotes. The prokaryotes means the primitive nucleus, and I am not supposed to say nucleus. The nuclear type of genetic material is there. And in the primitive organisms are in the early when the life started, basically. When the life started to grow, then the bacteria came, one of the early species. And when this happens, there was no oxygen, basically. They are full of lavas, magmas on the surface. The surface was hot also, not like today. And there are sulfides, methane, nitrates. And the bacteria have to survive with them only. And when the oxygen produces a very later time. Basically, some spark in the thunderstorm will also help to produce oxygen, which was later shown by Miller and Urey in their experiment 40s, the last 40s, maybe 80 years ago from today. So, and the prokaryote, there was no oxygen at that time. So they have to respire without oxygen, without any kind of oxygen, but this is for anaerobic respiration. Human also do anaerobic respiration many times. That's the one type of fermentation that is. But that is not a primary type of respiration. And when their oxygen is present, this is an aerobic respiration that we are doing in daily basis. And unless if we don't respire, we will be present today. So, and we also all know that oxygen is required for our respiration in daily life. So, why oxygen is required? Many of think that we take oxygen and we give out carbon dioxide and due to photosynthesis, plants take carbon dioxide and they give oxygen. But the process is not so simple because the formation of carbon dioxide has no role of oxygen. And the vice versa in photosynthesis. The formation of oxygen has no role of carbon dioxide. Oxygen is a final. Oxygen produces water basically in the system. It is a final electron acceptor. I will show you the following slides that how it basically accepts the electron and forms water. And in the following slides, we are seeing that various types of organisms that who takes oxygen and who does not take oxygen. So basically, oxygen is the mainly aerobic bacteria and any other living organism that respired with oxygen. And we can say that nitrogen, nitrites, and as well as sulfides and something SiO4 and human toxin and various type of microorganisms which respire without oxygen. But when the earth on the living system was evolving, some of the bacteria are also such as who can respire without oxygen, but will take oxygen if it is present in the atmosphere. I will talk about such a bacteria in the following slides, and you can see that what is the role of oxygen here. Here is the oxygen. Then you can see there is NADH which gives the 2 electrons, and the following cyclic photophosphorylation process, and here the 2 electrons is coming out. Something will have to take these 2 oxygen electrons. In our case, the oxygen plays a major role. It may be sulfur also, because in the periodic table we can see that after oxygen there is sulfur, which has in the outermost shell have 6 electrons and there is 2 vacancies. That O2 minus and H2 minus is formed. And what is that O2 minus is forming? There is some 2H plus is also forming in the other parts of distillation. This 2H plus comes and they form H2. The H2 is the outer product that form from the oxygen. And in the vice versa, in the photosynthesis also, water produces the oxygen product. That is separate issue. And now there are various of bacteria. So basically, we have taken the bacteria Klebsiella. Klebsiella is just a genus. I have basically worked with 2 types of bacteria. One is Klebsiella pneumoniae and this Klebsiella aerogenes. Why 2 types of bacteria? Because when the experiments were done and the data were present for us, it was done for Klebsiella aerogenes. But recently, we can see that our study was done in the tertiary care hospital in North India. Basically, a group of Indian scientists or doctors, they have done a survey or a test that how they have collected 82 samples, 40 in the first lot and 42 in the second lot after 5 years. So basically, what is Klebsiella? Klebsiella is a facultative anaerobic respiration. What I said before, that Klebsiella in absence of oxygen, but if oxygen is present, it will take it. But there is a condition. If it is strictly anaerobic, that no oxygen is present in the atmosphere, then it cannot respire or it is extremely cold. Then it will neither die or cannot grow. The bacteria have 2 modes of survival. Either it have to grow, and secondly it have to grow because the lifespan of bacteria is too small. It will just grow by the production of it. So if we cut that, then the bacteria will die basically. And this is the Klebsiella pneumoniae, and in the global in the same survey we have seen that the increase of resistance is amoxicillin. And now what is amoxicillin? You probably all have heard of penicillin, the first antibiotic that was discovered in the late 20s or early 30s basically by Alexander Fleming after the First World War. Then we have all know the story that he was researching on Sunday and just a fungi was dead in a bread, just suppose. But penicillin was the first antibiotic. Many of us know that several antibiotics discovered, but in today, thus penicillin works to any of the bacteria. So antibiotic also bacteria. It probably doesn't, because when the bacteria, we have taken the medicine on the bacteria. The bacteria also evolves or adapts. Basically, what is happening? Many of us in various news channels basically, they are told that don't keep the full dose, don't stop the antibiotics because the bacteria will get resistant to it. And what happened? That the resistance with amoxicillin is one type of antibiotic. That it is not resistant in 2022, and we are seeing there's an extremely dark resistance. Now what can we why we can know that a a bacteria is drug resistant or not. Basically, we have all known about RT-PCR in the past few years. The dangerous 2 years basically of COVID. The RT-PCR, the PCR, the polymerase chain reaction is one of the way to know the bacteria. We can know how the bacteria is resistant to how many of drugs. So basically, it is shown that 71 the bacteria 71% is drug resistant. It is about 71% of drug, which is quite dangerous because we cannot know what bacteria in India and another bacteria in Australia may have several drug resistance. And in that following it's a paper from 2021 that a global survey was done and the samples were collected from urine, respiratory tract by swab collection, blood and the overall view. That we have seen that the green part is susceptible. Means the bacteria is 50% susceptible to any antibiotics. But in the case of orange, the part is very large, nearly 40%. In the overall part, is nearly 42%. It is multi-drug resistant. It is a danger to us now. Now what we can do? There is two ways. That make antibiotic cocktails. The antibiotic cocktails that we can study this bacteria is does not resist this drug. We are giving the patient drug cocktail or produce entirely a new antibiotic. Now this cocktail process is done for very much long time. But you can know that in past few years, nearly 10 to 15 years, there are no antibiotics produced or discovered, rather discovered. So this is the this is basically the history of antibiotics. How this is penicillin and this is the last discovered antibiotics. And we can know that how antibiotics work basically. That the antibiotic works with one way that restricting both antibiotics. If this does not restrict, it will die. And another is that if we attack the bacteria by in the cell wall, we destroy the cell wall and the bacteria will die. In our work, we shall focus on the first part, that we shall try to restrict the growth or reproduction. So now is the how does bacteria respire? Basically, so there are three processes, and that the respiration is basically auxiliary one. If oxygen is more, it will respire more, not to a certain extent, obviously. And if it is less, then it will respire less. So basically, there are the three parts. In our process, if much oxygen is present, the respiration rate will fall down. And the second part, the oxidizable substrate, that is the nutrient, or bluntly we can say glucose. If glucose is present, so that also we can say that respiration rate also depends on the glucose present in the concentration. And also the chamber is done. That the oxygen to gas and gas to liquid and oxygen to gas transition in the following processes. So mainly there is two parts which we mainly focus on, that is oxygen initial respiration and uptake of oxygen from gas to liquid. Because in our human body we cannot restrict the bacteria to not to get food because it collects food from our body itself. So what does the first process transfer from oxygen to liquid? The rate of transport. It is basically dependent on TG, but TG is an oxygen tension is gas. You can assume tension and pressure, but basically the scientific term is tension here. You can assume it pressure, the partial pressure also. So it is the where A is the considered rate constant you can assume. So we are taking the assumption that in the first the oxygen assumption that is equals to the rate of oxygen from gas to liquid, because if you have these are some bacteria, which will take some oxygen and that much of oxygen will come from liquid to the gas to the liquid part. Because the respiration rate is so high. And what is the following? We can assume that if it is enough time of amount of reactant, the rate will go above. But it is not. It is formed by Michaelis Menten nearly 100 years ago, and probably we have done in our chemistry class in high secondary. The Michaelis Menten constant in various cases. So what is happening? The reaction rate will increase a certain constant of a substance. Glucose is present to some amount. Then it will increase, but then it will constant. But in our bacteria, what happening? It decreases after a certain level. That you can see. This is a graph of generally in normal cases. After certain saturation, it is saturation. After a certain level of concentration, it is saturation. But what is happening in the case of Klebsiella, we can see that it is going above, but it is decreasing after that. It is going above and it is decreasing after that. That is a very strange behavior of this bacteria. And we can see that we cannot explain why this is, because this is some kind of mechanism. But at a this point of view, we have to see what is happening with the liquid and gas. Yes, the DLNG, that liquid and gas relationship. But we can see that there is a hysteresis forming, that what bistability forming in this process. That it is basically a graph of F is the uptake rate, the oxygen uptake rate, and the tension of gases. So if we take a various K and a constant value, this graph is formed. The mathematical part of this graph is shown in later slides. So now the second part, the glucose part. If glucose at different oxygen that if oxygen is much more in the system, and what we have oxygen is very less in the system. So how do you think the glucose? We are not considering the glucose part. We are taking excess glucose in the system. So what's happening? We can see there is a graph. This graph is heavy because this paper is too old. You can see this from 1969, suppose. It's 1969. So the rate is increasing and then decreasing. That we have shown in the previous slide actually. So now, what is QO2? QO2 basically oxygen intake rate per gram of bacteria. That you can suppose that if bacteria is going up, then a respiration rate will go. But that's not the exact ground we are supposing. We are basically supposing that how much each bacteria, each unit of bacteria, each bacteria is very good thing. Each gram or each unit of bacteria, what is doing basically. So we are that is denoted by QO2, the oxygen uptake per gram dry weight. So now, what is if glucose in excess now, and now we are taking excess oxygen. In excess oxygen, what is happening? We can see the 95% of carbon. The glucose we all know that is H12O6. So it's basically hydrocarbon which is composed of carbon, hydrogen, and oxygen. And what is happening that glucose is producing CO2. Basically, the CO2 we extract is coming from glucose. So 95% of glucose is used, and 95% you can say it as laboratory some assumption that 95% is good enough. So it is producing basically carbon dioxide, pyruvic acid. Pyruvic acid is one of the byproducts. What is not completely oxidized basically, and some of the alcohol, the butane and ethanol. And this fermented process cannot be removed totally from the system. And because there is very much such oxygen level, very much high glucose level, so that all oxygen cannot remove the fermented product. And the destinatory portion basically volume of carbon dioxide and volume of oxygen. It is nearly 0.8. And what if we limit that oxygen, the oxygen density is going below 1 mm each. So we can see that fermented production is because it is not get enough oxygen to completely oxidize to CO2. But the interesting part in the middle, in every other cases we can see that there is a definite answer in two extreme cases. But whenever it comes to the transition case, we think that that some assumption or something got deep. And then there is something, the oxygen tension. But the oxygen tension, this is our oxygen tension we are taking, and we are supplying it for 48 hours. 48 hours is we are cutting generation. What does 13 generation mean? 13 generation basically means a bacterial reproduces itself 13 times. So, the most interestingly, what we are seeing, the first nitrogen linking group that we are giving the system oxygen and nitrogen. Nitrogen does not take any place in the reaction, but it releases the system. That it basically produces balance in the system. What is happening? We can see that in the limited nitrogen growth, that when glucose is excess, the first part is constant because now my oxygen is excess, glucose is also excess. But when the second part is coming, the limited oxygen order transition to the limited oxygen state. So it is happening. We are finding the oscillation. We are getting the oscillation there. So now, and in this case, we are taking that also the similar thing in the separate dilution rate also the growth rate. So we are getting a similar type of oscillation also there. But the main thing is there is oscillation. And this oscillation will get to our release like a basically the future slide. So now we are limiting the glucose because we have to organize the two things always. So if we take the glucose part, what is happening? The ammonium sulfate we are giving to the system as a nitrogen source. That the nitrogen limiting what I said in the previous slides. And what is seen that in excess of the limited glucose and excess oxygen, almost no fermented products are produced. All the carbon dioxide, because carbon is going to carbon dioxide, and the RE2, the respiratory portion is 19.02. That's we can see that the amount of glucose we are giving to the system, we are getting the whole energy from it. And now, in this graph, what we can see that the glucose, there is also less glucose in the system, and we can check the partial pressure of oxygen. If the oxygen density is less, we can see this is our desired graph. If oxygen density is less, the respiration rate is very less. But when the oxygen density is going up, it go to a certain level, then decreases, then a certain amount of oscillation, and then go to a fixed line. Fixed line, or I could say the process equals just by equilibrium position. So what is happening now? We are taking a transition state or a transition state. We are taking experiment for this, but ultimately we will see that experiment will not get successful actually, because we are taking a certain sulfate, because I have previously said that bacteria can also respond in sulfates. So we are giving a sulfate solution in some concentrations, but we cannot see the oscillation because the oxygen tension or the fluctuation in oxygen tension is very much less that it cannot be shown. And we can see here there is certain fluctuation, but at 8.6 to 8 mm, these are the millimeter of Hg of partial pressure, but the change is very much less significant. So we cannot do it in the sulfate process basically. We cannot observe it. So we are basically taking the nitrogen. So the system will have nitrogen as a liquid source, not the sulfate. So now in the oscillations part, we can get an idea. If there is excess oxygen is very much in the system, then it will keep the constant rate of oxygen up in the solution, because we cannot measure the oxygen uptake rate in the bacteria. We have to measure the oxygen uptake rate in the solution only. So in the transition state, we will get the when there is high oxygen tension. So there is a dissolved oxygen high. You can see that oxygen is gas is constant basically. It's the transition type of case. But when it is going, but in the same process, the oxygen uptake rate increases and the dissolved oxygen is going down. This is basically an oscillation part that is direction. That this part is the high state, you can say, and this part you can say a low state. So what happens? So this is the part of biology basically. The biology is an experiment. This experiment gives us some data, and they said there is oscillation, there is not. And now our biology is on a mathematics here. difficult to develop a system or a model how we can solve it or I can express it. So we are taking an analytic electrical circuit. We have seen various things. I suppose I have done it in my final year of bachelor's in something you can say that you're a dynamic molecule basically. And but you have to examine some properties about dynamic molecule. But you cannot have this lab for it, the exact lab for it. What we have done, then we have simulated in the electrical circuit. Now why electrical circuit? Because it is cost efficient and it is easily available in our labs. And you can see if the two equations basically follows the same rule, the same second order differential equation. Basically you can analyze both the systems. So in our parameters, so we have just kept these parameters used. That this is our electric system parameters. When these are current, and current is just repeated reaction just we said A actually in the previous slide. Sorry, the uptake we have said in the previous slide of oxygen uptake. And X is the external potential we are giving to the system, and this is the steady state reaction. Sorry, this is the reactant concentration in reservoir. That oxygen in reservoir basically that is what the liquid. This is oxygen in chamber, and this is the transport rate that K in our previous also I have shown it here T. So whenever we have done that we can see there is a differential equation like this. Now what this differential equation? We can assume that here is a dz dx and here is a dy dx. So dz dy. So if we examine closely that now if we take that we can say that if dz dx the previous slide is a maximum or minimum, right? Let us say extremum. Then dz dy and dz dy the both is also follow the extremum. So if we can see in zy plane, so we can say that if we rotate the tangent basically. So if the formation of a dz dx, if it has to be positive, then this dz dy have to be negative. And what we are observing from here, from this part, that's the K. I have basically you can say if it is minus, you can take that. Basically it is a minus. So dz dx is less than 0. And here it is infinity because it's equal. Basically the denominator will come to 0. The 1 by 0 is nearly infinity. And it is minus infinity and this is going to 0. Basically. Now we have to assume in an yx plane, yz plane, the hysteresis. We have seen the previous slide that is hysteresis basically. So from this we are observing the hysteresis part. So what the hysteresis part is meaning? That if we put this equation, this part, because this is a bistable solution of any system, or a nonlinear dynamic, you can say the imperfect dimension also from this part. So what is that happening in this Zx plane we are taking? The Z is the rate of transport basically. So we are taking a cubic solution. And if we are plotting this, basically a cubic equation basically a key solution. Two real. It may be one real, two imaginary, or it may be three real. So, if we adjust the parameter of E, adjusting the parameter of K, we are basically get three types of solution. And for K less than 1 by 8, if we put this in this equation and plot the graphs, that K part is 1 by 8, less than 1 by 8. So, we can get three solutions. Basically, there is even in the middle there is a fixed point and other two will be unstable. Here are fixed points, one is stable and other two are unstable fixed point. So now we can see that this term, this oscillatory term, we are seeing basically for oxygen part because we have seen the Y is the oxygen concentration in reservoir chamber etc. So basically we have in such a term and we are putting some coefficients here to just generalize it basically. So now we can go back to the biological system. What happened? There is a source of oxygen that is denoted with A and the source of nutrient that is denoted with B. And the oxygen, these are the sources basically. And oxygen and nutrient is shown by X and Y. So we can see that A to X and X to A, that is I can say that the oxygen is going from the chamber to the reservoir and the reservoir to the chamber. It is, we can say that, but the nutrient is one-way process basically. If we supply it to the chamber, then that's it. It cannot be taken back. So basically, if we take the rate constant, this, look at carefully this equation. This equation basically the change of oxygen, rate of change of oxygen in the liquid or in the medium, not in the bacteria. So the increase of K1 is the increase. Basically, we are putting something into the system. This is the K minus 3 is the decrease because we are taking out something out of the system. And this part is taken by the bacteria itself. The bacteria is taking some oxygen or some nutrient from the system. And what is the here it is? Here it is the plus Kb because there is no minus, there is no going back for the nutrient part. So it is that increasing by the outside system and decreasing by the intake of bacteria. So what is happening? So we are just trying to non-dimensionalize that term. Non-dimensional is basically a trick for nonlinear dynamics to decrease the parameters basically. That we are seeing that we are taking 5 parameters K1 to K5, and now after that we are remaining with some alpha, beta, and K. We have to operate. Basically, in this case, dx by dt, we just taking this, putting these values in these equations and taking back the two equations from here. So two equations that, and if we putting in zero, that it is state or a fixed point analysis. So fixed point analysis, we are taking that fixed point as such like x equal to a minus alpha minus beta and y equals to such thing. So now we have to we are trying to linearize the system around the fixed point. Basically, this is an assumption. You can see I am just avoiding this part. This is a higher order term. Basically, we have all that in data science expansion. The higher term, we are just neglecting, and we are neglecting it. And then what is happening to the Jacobian part? The what is the Jacobian? Basically, we are taking this because it is basically you can take the first order differential terms, and the form is like this. And when we are calculating the fixed point x and y, we are getting back this term of this. And we can see this is almost a similar type of matrix because in the following slide I will show why. And now, if the basically the nonlinear dynamics technical point, trace is less than 0. Basically, you can say the energy eigenvalue basically the energy trace, the sum of trace is basically the sum of the eigenvalue. When it is less than 0, it is a stable system. So basically, whatever we have done, this is the, we can say the secular equation from the whenever we do any eigenvalue solution, we get such kind of equations, and this is basically a energy eigenvalue. If we get observe this eigenvalues are real, if this discriminant is greater than or equals to 0, where it is such terms, and now we can see that this term is obviously less than is greater than 0. So this term is greater than trace of j because this term is something less than trace of j. So this is also negative and this is also negative. So we are getting alpha lambda 1 and lambda 2 is also less than 0. So now, and for the complex system we have done this similarly, that we are taking the real part basically. So now we are taking the test and got the test equations, and now we are getting the determinant part. So whatever this that I have said that this is almost symmetrical. Then basically j1 minus 1 and this part will get to this equation, and we know that determinant should be greater than 0. So the denominator is definitely because positive. Sorry, it is definitely positive. So using a square. So from the numerator part we can get alpha greater than beta. And this condition we are putting in the case equation. And why this is happening? This equation from K you can get it. And what is happening is we can see K is always positive because it consists of rate constant. Rate constant cannot be negative. So this is also positive part. The numerator is also always positive. This is also positive. So it of course have to be negative. It of course have to be positive. It is positive and this of course have to be alpha less than 2 beta because it is also have to be positive. So now what is happening? What is happening? We have just checked the two conditions we have. Now it is a parameter we are getting from linear solution. Now if we do some non-linear solution, what we will get? That we are simulating it by sixth order Argand method. And firstly, we have seen for taking beta equals to 5 and alpha is between 5 and 10 because beta is between alpha and 12. So we are taking 7.5 and K equals to 0.5. For stability, we have to take 0.8. But we are very fixed point. What is good? Good on the theoretical solution. And for also this case, we are getting an limit cycle for the two cases that we are destroying the stability because the stable condition is kappa less than this amount, and we are getting 0.5. Well, now the tricky part is coming. That if we with the previous parameter we are giving, even if we give a kappa equal to 0.359, I also get a limit cycle. And if we are getting 0.55, we are getting a close to 6 point, but we are observing a metastable state. The bacteria is in this system for a very high time, basically, and then it goes to the fixed point. So what is happening? So in the non-linearized approximation, we have just avoided the higher order terms. So the deviation for the theoretical calculation is coming from this, basically. So what is happening that what can we do from this? This I have basically taken two bacteria. Is anything else. So we are giving some noise so that we can destroy the limit cycle of the fixed point. And what is the next part? And we can just check that numerical data that we have seen all the time or alpha or beta in all parameters. They are in non-dimensional parameters, not real parameters. We can put the real parameter K1, K2, K3 and get the original time. How much the medicine is work, or how much the limit cycle is work, or how much the medicinability is work. And the final part, this work will give the new discovery of antibiotics because it is a very interdisciplinary work. This work may be done by any material scientist or any medical scientist or anybody or biologist. Basically, ultimately the bacteria is getting drug resistance. That we have to give some more antibiotics to destroy it, or we cannot be survived at all. So from the references, I have just basically the key references from it. This is basically the differential equations from this Iron and Faraday model. This is basically the pioneer for this work. And these two papers are basically the recent data, the 2021 and 2023 data for the text data. And the rest of the for the biological parts and the chemical reactions I have. And I acknowledge my supervisor, Professor Mukti Sajai, and my friends for this work. And thank you.
So our biopharmaceutical companies are using this problem. What are the researchers in the biopharmaceutical research companies using this problem?
You can see that we can something we can do that destroy the limit cycle. Because this is a cycle that oxygen is getting less, but at certain time the process is going to back. It actually is certain. We can do that this limit cycle is broken. One of the part is this. What is the principle? If there is a principle, we can stop it. By some external agent. External agent we can use medicine or chemical agent. So we can study that. Here we can study the non-parameter. We cannot say that this medicine, but this chemical. But we can predict this mathematical behavior basically. So we can do it from mathematical part. By changing the different cycles.
As for the third reference in the slide, which tertiary care hospitals in North India were targeted for their study?
No,
Any research and which state are there? What are these?
No, this is there is a North India. They are collected from various hospitals, not a single one.
No, the participating institution. Research.
No, I cannot research.
Then I will
Yes, you can see.
Thanks for being very kind.
Thank you, Shobhatu and Shobhati, for such an interesting talk. As we proceed towards the last talk of this session, I would like to invite Ishika Chikadar, a PhD student from Presidency University, Kolkata.
Good evening, everyone. So it is afternoon session. Now it's time to welcome the next and final speaker, Kobi Chatterjee, our one of student in Presidency University Physics Department. Kobi has recently completed his master's degree from this university, currently working as a project fellow at ISI Kolkata. He will be talking about lots of Volterra model of competition.
Hello. Am I audible to all? I hope so.
you.